continuous, if a function is continuous, and at some moment of time the function is negative, at some moment of time it is positive, somewhere in between it must be close to the point 0. Somewhere in between it must be 0. And last thing we've seen that this property, this intermediate value theorem, can be applied to two, well, somewhat different situations. One situation is when you have an actual function, say something like x cubed plus x minus 5. And you want to find out whether this function is ever equal to 0. And the way can find out whether the function is equal to 0 is find one value of x where the function is negative, one value of x where it's positive, and then intermediate value theorem, because the function is continuous, tells you that somewhere in between the function is equal to 0. And we've seen, well, an argument how, given a large interval where we know there is a 0 of this function, how to narrow down to really small intervals. And it was all just application of intermediate value theorem. So that was the quantitative application of intermediate value theorem. We've also seen some qualitative applications. And these are about applying intermediate value function, intermediate value theorem, not just to one concrete function, but rather to a class of functions with given property. In the very end of last class, we talked about an application of intermediate value theorem, which was like this: if f of x is between 0 and 1, for x between 0 and 1, and f is continuous, on the interval from 0 to 1, then there is x such that f of x is equal to x. So that was the last example we discussed on Friday, and I won't recall exactly how we solved this question. I'll just recall what the picture was, because somehow in the end of last class I devoted just 15 seconds to the picture, but it deserves more attention. So this question is not talking about one concrete function. It talks about a class of functions which have some property. And the property is like this. It sends number from 0 to 1 to numbers from 0 to 1. If you put in a number from 0 to 1, the output is going to be a number from 0 to 1. And naturally, we cannot really argue what the graph of the function is. We have no idea. But we can argue about, well, in general words, what the graph should look like. So here's what I mean. The function takes numbers from 0 to 1 to numbers from 0 to 1. What does it mean about the graph of this function? Well, here's this square from 0, 1 to 0, 1. And if you put in a number in this interval from 0 to 1, the output is going to be a number from 0 to 1. So the whole graph of this function, this the part for which x from 0 to 1 is contained in this square. It never goes above this line, never goes below this line. So I don't know, what something like this might go like all the way up and all the way down, might not go, might be always increasing, I don't know, but for sure it is contained in this square. Now, what are we looking for? We are looking for a point x where f of x is equal to x. So on this graph of the function, we are looking for x measuring between 0 and 1. That's the only numbers for which we know something at least about the function. With the property that f of x is equal to x. So how can we graphically on a picture understand what this point is? Well, on the graph we have graph of f. These points where y is equal to f of x. And here we want to find such a point on the graph of the function where this y coordinate f of x is equal to x coordinate. And we know how all points where x coordinate is equal to y coordinate look like. It's the line x equal to y, or y equal to x. So it's this line. So we are basically looking for a point of intersection of the graph of the function f with the line y equal to x. That's all we are doing. And now once you see a picture, it becomes more or less obvious what you should do even algebraically. So our argument would be like this. Our function at point 0, well, it is from 0 to 1. So wherever it is above this line, above the line y equal to x. Because this line right here is 0, f of 0 is above it. It's from 0 to 1. On the right hand point, my line y equal to x goes through point 1, 1. The graph of the function passes below this point, because f of 1 is from 0 to 1. And this line is continuous. I can draw it without taking the chalk off the board. Hence, somewhere in between it must cross this line y equal to x. And you should recognize that these kind of arguments, the graph of a function is below something on one endpoint, above something on the other endpoint, hence it must cross this something in between, is exactly the application of intermediate theorem. Except here, we didn't want to cross the x-axis, we wanted to find a point where the graph crosses the line y equal to x. So if you want to actually apply intermediate value theorem, you would have to solve instead of this equation, an equation of the form something is equal to 0. And then we came up with a trick of rewriting this equation in the form f of x minus x is equal to 0, and then rewriting these arguments so that they resemble the intermediate value theorem much more. They become just an application of intermediate value theorem. But basically the intuition should be this. We are looking for a point where the graph of the function crosses the line y equal to x. And the way we do it, well, on the left hand point, the graph of the function is above the line, and the right hand point is below. It is continuous, hence somewhere in between must cross. So now I want to discuss maybe first questions about this picture. I want to discuss a question which looks even less similar to intermediate value theorem. So here's the question. No problem. Show that at any given moment of time, there are two antipodal points on the equator with exactly the same temperature. So we know that Earth isn't in fact something like a sphere, maybe you saw it, but something like this, and has an equator, a line which divides the Earth into halves. Well, imaginary line, of course. And the question is about 2 points in this equator, and antipodal means they are exactly opposite to each other. So if here's 1 point on the Earth, then antipodal point would be that point. So you have to connect this point to the center of the Earth, draw a line, and on the other side of the Earth, you'll find this antipodal point. So the question is, show that at any given moment of time, let's say right now, there are 2 points on the surface of Earth, on the equator, such that the temperature, and they are opposite to each other, such that the temperature at one of them is exactly equal to the temperature of the other. Okay, so let's start thinking about this. Even before I start, has anyone seen a similar problem? Okay. Any ideas whatsoever, not necessarily an actual solution, but any thoughts about the problem? Does it sound likely or does it sound unlikely? Does it sound surprising? Does it not sound surprising? Just any opinions?
It's likely.
It's likely. Why? Do you have any indications about it?
No, it just seemed like it'd be very likely.
Okay. Any other opinions?
Well, one side would be affected by sun, the other side might not. So that could cause
yeah.
temperature.
Okay. So it is evidence to the that this is right, or evidence that it's wrong?
That's wrong.
That's wrong. So in your opinion is, so on one side of the Earth we would expect to be day, on the other side we would expect to be night, so we would expect that on one side it should be warmer than on the other side. Yeah?
Wouldn't it be dependent on time because if the Earth rotates, then at some point or another, the two opposite points would be the same distance away from the sun?
Yeah.
Okay.
Makes sunrise.
So, in your idea, well, it does sound likely that like during the daytime it's warmer than during the nighttime, but there are points somewhere in between day and night, and maybe they are actually on the opposite sides of the Earth, maybe or maybe not, and it's likely that as time goes by, these points will shift. Okay, yes. All these thoughts are correct, and this question is not saying that there are 2 fixed points which do not change with time. But just if we kind of freeze the time right now and go all over the equator, we will be able to find 2 points which are opposite to each other and having the same temperature. If we freeze into hours, these 2 points might be quite different. Okay, so that's one thought, that we actually should think about just one moment in time, not about how these points change with time, but rather just one point in time. Second thought was, we know something about the distribution of temperature on Earth. Well, it might be true, might be not quite true, because you know, sometimes it rains and the temperature drops even during the daytime. Sometimes there is a wind from the desert and the temperature rises during the night. So you can't really be sure that at every given moment of time there will be some warmest spot on the Earth, some coldest spot on the Earth, and the temperature will go down from the warm to the cold part. But it is some beginning. At least we can imagine some typical temperature distribution. So somewhere it's probably very high, somewhere it's probably pretty low. And if you want to find some points which are opposite to each other and the temperature is the same, then maybe we should look somewhere in between the maximum, the largest point, the warmest spot and the coldest spot. Okay. Maybe any other thoughts? Okay, so let me try the following. So, to be honest, when I look at this statement, just look at this statement, I have similar thoughts to, well, to the one expressed somewhere here. And I think about the Earth, I think about like, okay, so we have a warm point somewhere, let's say here, cold point somewhere there. Why should there be a point where the temperature is equal? Well, I start thinking about points where it's kind of somewhere between morning and evening on one side of the Earth, and somewhere between morning and evening on the other side. I think about points having the same temperature, but I see no apparent reason why it must be exactly opposite to each other. Maybe both like closer to the warm point. Kind of sounds unlike. And then in my mind I start thinking about, well, maybe I can construct a counterexample to this statement, which would mean maybe I can imagine such distribution of temperature on the equator so that there are no opposite points with the same temperature. So I try to imagine how it might be possible. And well, so suppose I try to construct an example where the temperature on the opposite side of the Earth is always different from the temperature at the point on this side of the Earth. So let's pick a point here and look at its opposite. The temperature here, well, it's either higher than the temperature there, equal, or smaller. If it's equal, we are done. If it is higher or smaller, well, let's see what happens. Let's say that actually the temperature here is higher than the temperature here. Let's now start thinking about how we can extend this temperature distribution all over the circle. So first of all, the Earth itself doesn't matter. We are only looking at the equator. So let's imagine just the equator. And let's imagine that the temperature here is actually higher than the temperature here. Then I imagine myself walking along the equator, and my kind of an antipode of me, so somebody who is walking at the same rate on the opposite side of the Earth, and we are communicating over cell phone. I tell him the temperature here is 30 degrees Celsius. And he is telling me the temperature here is 10 degrees Celsius. I walk a step, he walks a step, and we communicate once again, and we wait for a moment when we'll communicate the same information, same temperature. So how could it be? Let's say here I have high temperature, here I have low temperature. I walk a little bit to there, he walks a little bit to there. We communicate once again. It might be still true that the temperature here is higher than the temperature here. And it might be true that all over this interval the temperature is higher than the temperature there. What's not possible, if I want to construct a counterexample, is that here I reported the temperature which is higher, and here I will report the temperature which is lower. If this is the case, so if the temperature here is higher than it is here, but one step after it is lower than the temperature there, then somewhere in between, the temperature must be the mean. That's basically our intuition behind the intermediate value. Okay, so if I don't want to have any point, any pair of points which are opposite to each other and where the temperature is equal, I must agree that if here the temperature is higher than there, then here it is also higher than there. So I'll continue doing this thing. I'll move from here to there, and he will move from here to there. Once again, same argument applies. If I already argue that the temperature here is higher than the temperature here, I must also agree that the temperature here is going to be higher than the temperature here. Why? Well, if it wasn't, if the temperature here was actually lower than the one here, then somewhere in between, it must have been equal. Okay. But now nothing prevents me from performing the same kind of reasoning over and over and over. So I go from here to there, he goes from here to there, and I argue that the temperature here must be higher than the temperature here, if I want to construct an actual counterexample. Well, I'll move one extra step, still the temperature here must be higher than the one here. New step, new step, new step. Still the temperature here must be higher than the one here. Just because I apply the same kind of argument over and over and over. Well, what's going to happen when I will come back to the spot where I started? Does anyone see what happens now? Yeah?
Well, if you get back to where the other person started, which then theoretically the temperatures are the same, or the difference is the inverse of, like, originally say you had a difference of A, well now it's the difference is negative A, so then you should have passed a point.
Exactly. So what happens is I return to the same point, I came to a point where my antipode was in the beginning. I know already that here it is colder than it was there. And he came from a cold point to a warm point. So in fact we have the same kind of argument. I walked from a warm point to a cold point, he walked from a cold point to a warm one. Somewhere in between we must have crossed a point where our temperatures have been equal. So if I imagine a graph, let's say x will be my walking distance, and here I'll have two functions. One is the temperature reported by me, and the other one is the temperature reported by my antipode. So somebody who is exactly opposite to myself. What happened is we started with something like this. My temperature, reported temperature, was higher than his. We went and went and went along the equator. We agreed that we are reporting the temperature at every moment in time. Maybe it went up, maybe it went down, maybe it went up one for me and went down for him. I don't know what happened in between, but once we reached half the distance along the equator on the Earth, we are back to the initial temperatures. But I'm back to his temperature, and he's back to mine. So his report crossed from this point to that point, and my report crossed from this point to that point. Is there a way to connect this point to that point and this one to that point without the graphs ever crossing each other? Well, no. So if I want to connect this to this and this to that, there must be a point somewhere in between where the graphs will cross each other. Okay, so now it does look like an application of intermediate value theory. We are arguing about the intersection of two lines, and the kind of argument is at one moment of time, or at one moment, in this case, of space, one line is below the other, at the other point, it is above. Well, once again, intermediate value theorem applies not to a pair of functions, but to one function, and this function being equal to 0. So let's now formulate mathematically precise argument. So I want, first of all, from this intuitive argument, it's obvious that I will be applying intermediate value theorem. Next question is, what function would I be applying this theorem to? Yeah.
Would be the difference between the two.
The difference, yes. So I want to reformulate the equation of two temperatures being equal to each other as equation of some function being equal to 0. And this function is obviously the difference between the two temperatures. So let T of x be the difference between temperatures at point x and its opposite point. On the equator. So now I have a function. At every point, it measures the difference between temperature here and on the exactly opposite point on the Earth, on the equator of the Earth. Okay, so I have this function. Let me also choose what this number x is. I want to think about x as a number, so x or location of the point x will be measured or recorded as it is. So for a point on an equator, it makes sense to talk about its longitude. So something like this. There are meridians, lines, imaginary lines going from the North Pole to the South Pole, and there is 0 meridian. Then you have 10 degrees meridian, negative 10 degrees meridian, and 20, plus 20, and so on. And the whole Earth is from longitude minus 180 to longitude 180. So 180 is the exact opposite there. So now we have a function. For every longitude on the equator, it tells what's the difference in temperature between this point, let's say T of 0 would be the difference in temperatures here, longitude 0, and the opposite point, longitude 180. Okay, now next thing. I want to argue that this function has different signs as x goes from one side of the Earth to exactly its opposite on the other side of the Earth. So let me make this argument like this. Here's T of 0, and the other thing would be T of 180. 180 is a point exactly opposite to the point with longitude 0. So, what can I say about these things? I claim that these things have opposite signs. Why? So it's basically a question about whether I explain clearly enough what this function t is. So I claim that T of 0 is the difference between the temperature at longitude 0 and the the temperature on the opposite side of the Earth, which is longitude 180, has opposite sign from T of 180, which is the difference between the temperature at longitude 180 and its opposite, which is the temperature at 0. Is it now obvious why we have different signs?
Unless they're already the same.
They are exactly the same but with opposite signs. So T of 0 is difference in temperatures between longitude 0 and longitude 180. T of 180 is difference in temperatures between longitude 180 and longitude 0. So the opposite longitude 180 is 0. So T of 0 is in fact the same as T of 180, but with opposite sign. If the temperature at longitude 0 is say 30 degrees and it's 15 degrees on longitude 180, then T of 0 would be plus 15, 30 minus 15, and T of 180 would be minus 15, 15 minus 30. Well, this function is continuous, and this is some physical assumption. It's not mathematical, it's physical assumption. It's plausible to assume that small change in position will lead to only a small change in temperature. That the temperature doesn't change abruptly from one place to a place right next to it. So T x is continuous. That's plausible from physical assumptions. Well, conclusion. Hence, by intermediate value theorem, T of x is equal to 0 for some x between 0 and 180. So maybe I should draw a little bit better picture of the equator and the longitudes along the equator, so that you won't be confused by this 0 and 180. The longitude works like this. There is some longitude, some point where the longitude is 0. Here the longitude is 90. Here it's 180. Here it's minus 90. And at this same point it would be minus 180 or 180. There is some infinity above. So what we argued is at every place we measure the difference between this temperature and the opposite temperature. If we start at 0, we get some number. It's either positive or negative. Regardless of what it is, as we go along the circle and come back to here, the difference is going to be the same, but with the opposite sign. So since it went from positive to negative or from negative to positive, it must have been 0 in between. That's the argument. So, questions about this example? Yeah.
So, because G
which one of them is positive and which one is negative, but we are sure that they have opposite signs. So one of them is, or maybe both is zero. If both is zero, then they're done. If one of them is positive, then the other one is negative, hence the function somewhere in between must have been zero.
Okay, so we can't figure out the exact equation, the exact numbers, but we know what it should be.
And we really don't know, we didn't make any assumption about the actual distribution of temperature on the air. We didn't know that, I don't know, on one side during the day it's warm, on the other one it's cold. We didn't make any assumptions whatsoever. Our only physical assumption was that the distribution of temperature is a continuous distribution. No sudden abrupt changes, which is very plausible. Otherwise, we assume nothing. Not even that the temperature is, I don't know, always small and between these Celsius. Nothing, just nothing. And of course, you can see that, well, our argument doesn't tell anything about the location of this point where, of this pair of points where the temperatures are equal to each other. So if we try to apply the same argument at a different moment of time, we might as well get quite different points. That's exactly why it applies to your first question about how does the point depend on time. Well, this argument tells you nothing about how it depends on time. It might be changing from one moment to another. But at every moment of time, you can apply this argument and get at least one pair of points which are opposite to each other and temperature is equal. Other questions? All right. So we talked about continuity, and we've seen that continuity is, well, a useful property. For example, the continuity can prove such interesting statements. And remember that continuity was basically about the relationship between a change in the argument of the function and a change in the value of the function. If the change in the argument of the function is small, for a continuous function, the change in the value of the function will be also small. So continuity was about, well, qualitative side of this thing. Just a small change in argument leads to a small change in the function. The next concept, the concept of derivative, is going to be about quantitative relationship between change in argument and change in value of function. So let's talk about this notion of derivative. So the concept of derivative is about the following thing. If I believe my function at 2 points, x1 and x2, I can measure how much the function has changed between x1 and x2. That would be this difference. I can also measure what is the change in the argument. What is x1 minus x2. If the function is simply continuous, I know that if this is small, then this is small as well. Now, next question is, how do they compare to each other? Can we say that this is roughly, I don't know, 5 times this one? If you have two small numbers, you still can ask a meaningful question, how large is one of them compared to the other? And the measure of this would be such a quotient. The difference in values of the function divided by the difference in values of the argument. And in fact, we have already seen such a quotient. If you recall, what is this thing? This is the average rate of change of f is its argument goes from x1 to x2. So we are already familiar with this quotient, change in values of the function divided by change in values in the argument. And recall that when we talked about the average rate of change of the function, we also started talking about the instantaneous rate of change of a function. What happens when this point x1 is really, really close to x2, when this change in argument is really, really tiny. So recall that as x1 or x2 approaches to the point x1, this quotient f of x2 minus f of x1 divided by x2 minus x1 approaches what we call instantaneous rate of change of f at x1. So this instantaneous rate of change is about the following thing. If you change the argument just very, very slightly from x1, how much the function is going to change. And this is measured by such a quotient. The change in the function, which is a really small number, but then divided by this tiny change in its argument. And this quotient of two small numbers, well, it has a chance of being some meaningful number. Something not really tiny, something like 5, some actual number. In other words, now we can make a precise definition of what this instantaneous rate of change of a function is. More precisely, instantaneous rate of change of f at x1 is now we have a very precise way to formulate it. This is the limit as x2 approaches x1 of this quotient. So now we have to combine now two concepts. One of limit and one of this average rate of change and instantaneous rate of change. So recall that limit of whatever expression is what the expression approaches as well, the variable in the limit approaches the value in the limit. So in this case, as x2 approaches x1, the limit is about what this expression approaches as x2 approaches x1. And this expression being the average rate of change of the function from x1 to x2, as x2 approaches to x1, this thing approaches the instantaneous rate of change of the function at the point x1. And finally, we give a name to this answer. So the name we give to it is like this. We call it f prime. And it's just, well, basically a name notation. F prime is the instantaneous rate of change of the function f. And we also write at what point. So we write f prime at the point x1, and this would be whatever this average rate of change f of x2 minus f of x1 divided by x2 minus x1 approaches as x2 approaches x1. So before even we see our first examples of computing this thing, the instantaneous rate of change for f prime, like we outline the different points of view on this thing. So probably won't even have time for an example, so let me just word it to tell the following. So f prime of x1 has the following meanings. First of all, it has a name. It's called derivative of f and x1. This word, well, for now is pretty meaningless. It's just a name for this thing, for this number, f prime of x1. A more meaningful thing would be what we discussed just now. It's instantaneous rate of change of f at x1. Another interpretation. This quotient, if you recall a picture, was the slope of the secant line passing through point x1 comma f of x1 and x2 comma f of x2. As x2 approaches the point x1, secant lines become closer and closer to the tangent line of x1. So this thing is also the slope of the tangent line to graph of f at point x1. X which is equal to x1. And finally, one last thing. It is about the following thing. If x2 is approximately equal to x1, then the change in the value of the function f of x2 minus f of x1 maybe is approximately, well, it is proportional to the change in the argument, and the coefficient of proportionality is exactly this number. So whenever the change in argument is really small, when you have 2 points which are really, really close to each other, then this number is exactly, well, is more or less such a quotient. So the change in the values of the function is proportional to the change in the argument and the coefficient of proportionality of this derivative. So we see that this thing, well, has lots and lots of interpretations. It is really important. So next time we'll talk about how to actually compute this.